Hi there, BC Calculus students, and we're looking at the idea now, the introduction to limits. So the limit of the function is the y value that the function approaches, but specifically it's a value that the function approaches as the function input gets closer to specified x value. So for a limit to exist, then the y value, the function is getting close to from the left-hand side of that value x, and the right-hand side, the value that the function's approaching, again, the y value, the function's approaching from the right, those have to be the same. And if they are the same, which may or may not even be the function value, we say the limit of the function then is that y value, whatever the case may be. So there below, I've symbolically represented that limit of f of x as x approaches c from the left. That negative sign is actually says as x approaches c from the left has to equal the limit of the function as x approaches c from the right. And if that left-hand limit and right-hand limit are not the same, then we just say the limit does not exist for a particular function. So we have been dealing with, excuse me, I got to get back to the iPad, needs to come back up here. We have been toying with the idea of limits here in section 1.1, and with maybe you know realizing it or not, but this is probably the basics of all of calculus. We proved later on derivatives using limits. We proved later on integrals using limits. The length of that curve again using limits. So a pretty big concept that comes up, especially in the first two units primarily, but then throughout the course as we continue to study. So as we look here, then I want to go over a couple examples in day one. Excuse me. Day one, example one. We're using what's there, a difference quotient, and that is a term I want you to recognize. And there are a couple of different difference quotients that I can actually take a look at. I can take at, and we're doing this actually with a right difference quotient. We could also do it with the left, or I can use a symmetric difference quotient. So in example one, we're picking some t values here. We've got this function here, 16t squared, which is represented at the 16 is half of 32, and 32 is what Newton decided was the force of gravity. So 32 feet per second squared for acceleration, and then that's value 16 is half of that always. So S of t, this is almost a position function, but telling me basically how far the object has fallen after t seconds as well. Okay, so from a situations as this, then I want to approximate what the S5 is, and I'm not so much do I want to approximate S5 as I want to come up with how fast it's actually changing, what the speed is going to be, the velocity is going to be for the first 5 seconds. So I first of all picked an interval from 5 to 5.1, and then an interval from 5 to 5.001, and a 5 to 5.0001, just a 10,000th of a second past 5. So we're going to look at, again, the velocity here, not necessarily how far it's traveled, but the velocity here, which is in essence going to be the derivative of 5. And I'm going to do that with those approximations. So I'm going to encourage you to look at that chart, but what I want you to realize in particular is that it's S of t minus S of 5 over t minus 5. This is, again, the velocity of the object at 5 seconds. And well, it's even better perhaps to say it's an approximate value of the velocity at 5 seconds. So this isn't a new formula for you. You look at it and it looks a whole lot like slope. You also notice that it's just the distance, the change in the distance. And in calculus, you'll often see me use delta something, which is the change in over the change in the time. So, and that of course is the rate, or in this case, velocity. So just wanted to highlight a couple of those things. Again, I used a right difference quotient. A left difference quotient, I would have used values less than 5 to approximate it. And a symmetric difference quotient, I would have used values on either side of 5 and kind of squeeze it in as I go to 5. That in that same section, we have a AB question from, excuse me. We have a question from the AB test in 2018. These don't change a lot in terms of the type of question that's being asked, and this is a kind of a favorite of them. They like to represent things graphically and from tables and basically analytically. So this is a case here where we're given a table, and you notice it wants to know how fast the tree is growing at approximately 6 years. So that H prime of 6 will represent how fast the tree is growing at 6 years of age. And it doesn't necessarily say what the height will be at 6. It just says how fast it's changing, how fast it's growing at 6. So I'm going to approximate that. You'll notice that the H of 6 isn't even in the table. H of 5, H of 7 is. So I am going to use that symmetric difference quotient and say that that's approximately H of 7 minus H of 5 over 7 minus 5. And again, you should hopefully recognize the similarity between those two formulas. Again, the change in this case, the height over the change in years. So as far as, excuse me, this is in meters now. But the idea then being, again, approximately how fast the tree is changing. Those values, again, from the table would have been 11 minus 6 over 7 minus 5, 5 over 2. I would answer this question in the following manner. Then I would say something like this. The tree is growing at a rate. Since it's positive, it's growing at a rate of 2.5 meters per year. Okay, when the tree is 6 years old. Now, this answer is kind of a standard type answer I wanted you to get accustomed to writing. It follows the nut. acronym that I use. I've got a noun and a number. I've got units involved. And I have at a specific time or time interval. So within that answer, whoops, my noun, the tree, and also the number, I have a specific unit that I'm looking at. In this case, meters per year. Not surprisingly, this was the difference of meters and this was the difference of years. Meters per year. And then also at a time, particularly when the tree is 6 years old. So a noun and a number, the units, and then a time or later on, a time interval that represents then specific to that particular problem, how fast the tree's growing at 6 years old. So from almost day one, not quite, we're looking at the idea of applications of from like AP tests. So you will see these throughout our notes, past AP problems that I'm bringing in and work with you on as part of the notes as we're ready for them. So didn't take long though to get into that mode. So day 2 actually has a problem in it, and I'm going to try to bring this up and see if we can do this. And hopefully there it is. Yeah. Let me share a little bit more over here with the Desmos. We have that function x cubed minus 1 over x minus 1. Of course, if you remember your SOAP factoring, that does cancel. I'm going to show you that to you in a second. But here's the graph of that function. And again, we're using the idea of a symmetric difference quotient to see as x gets closer to 1 from the left, or as x gets closer from 1 to the right, where is the function going? And it looks to me, and graphically and or from the table, that it would be 3. And I know that you've got some things there, but as x goes to 1, again, those functions are getting closer, or the value is getting closer and closer to 3. So since the left-hand limit is 3, as x approaches 1 from the left, the function is going to 3. Since as x goes to 1 from the right, the function is going to 3. I say the limit of that function is going to be 3. We can look at that also from a standpoint, if I do a little factoring algebraically as well, we know that's x minus 1. Oh, well, let's try that again. X minus 1 times the quantity. Again, use your SOAP. Same, negative, opposite, always positive. And then the x minus 1 over itself, I won't say it cancels, but simplifies to 1. And therefore, if I now look at, change this a little bit slightly, that limit of x goes to 1 of x squared now plus x plus 1. And if you do direct substitution there, 1 plus 1 plus 1 is going to be 3. Again, and we can do that algebraically as well. So we'll look at that a little bit more. And then into day 3, there again is that idea, left-hand limit has to equal the right-hand limit. In example 2, it's pretty clear the left-hand limit is limit as x goes to 1 from the left is -1. And the limit of f of x as x goes to 1 from the right is +1. Since they're not the same, I'm going to say the limit as x goes to 1 of f of x does not exist. Now, if you look at example 4, left-hand limit's 1, the right-hand limit's 1. The function's not 1, however, but that's a different story for down the road when we start talking about continuity. But the limit still exists at 1, even though the function's not 1 there, and that limit would then be 1. And then example 6, another possibility, you have a vertical asymptote there at x equals 2. As x goes to 2 from the left, it goes to -infinity. As x goes to 2 from the right is +infinity. Again, the limit doesn't exist. Left-hand limit not equal to the right-hand limit. And so therefore, once again, we'd say the limit doesn't exist. And so there are 3 reasons the limit would fail to exist. Left-hand limit's not equal to the right-hand limit is 1. And then these are in that red box there in the day 3 notes, that it goes unbounded. And again, that could be both positive or both negative. But even though, and then we have to split some hairs here and talk about a limit going to infinity, and we'll do that. I want to be just describe that with you in person probably. But and then also you'll see some cases where you have some oscillation there, some functions that are a little bit different from what you've seen. Again, involving where the function is not going, it's going back and forth between values, and you can't say it's going to a specific value, only one value, and therefore again the limit doesn't exist. So you'll see that come up as well. We'll look at continuity later, and then on the next video I'm going to still talk a little bit here about the idea of composite functions and how to find the limit in that case. That's just a little bit different scenario than these first ones, so I'm going to hold off on that just a little bit, but I think it's would be something we want to do, and again a separate video. So that's it for today. Again, take care of yourselves. We will pick up again with the composite functions and involving limits next time. And have a good weekend, and we'll see you soon. Bye now.